this year's Mathematical Physics Days. My name is Shelale Shahin. I'm a PhD student in Boğaziçi University, and I will be the chair of today's morning session. We have three talks that will be given by Todor Popov, Osman Teoman Turgut, and Meltem Ünel. As to remind you, each talk will take 40 minutes and will be followed by a Q&A session for 10 minutes. You may ask your questions using the chat feature of Zoom and we will deliver them for you, or you can unmute yourselves and ask your questions directly. So, Todor, meanwhile, let me briefly introduce you. Todor Popov is an associate professor at Bulgarian Academy of Sciences and adjunct associate professor at American University in Bulgaria. He obtained his master's degree in physics from Sofia University in 1997 and his PhD in mathematical physics from University Paris 11, France, and Institute for Nuclear Research and Nuclear Energy, Bulgaria in 2003, under supervision of Ivan Todorov and Michel Dubois-Violet. He continued there as a research fellow in the Theoretical Physics Division in 2004. He earned NATO and ANR grants and held a postdoctoral research position at Centre de Physique Théorique in 2004. He became associate professor at INRME in Sofia in 2015. He earned TÜBİTAK Fellowship for Visiting Scientist and came to Koç University between 2015 and 2016. He was a visiting scientist at Trieste University in 2017 and at LPT Orsay in 2019. His research interests include representation theory, non-computative geometry, quantum groups, and Hopf algebras, and so on. And today he will talk about hydrogen atom and spacetime symmetries from Van Jordan algebra. Todor, I will warn you at the last 5 minutes, and you can start if you're ready.
Thank you very much. Thank you very much. It's my great pleasure to be invited and to be part of this conference. As you told already, I have been in Istanbul. I was there invited by Professor Tekinder Ali. I keep very good memories for the long, inspiring discussions in his study in the Koç University seminar, also the Boğaziçi University seminars in physics and in the Center in Mathematical Sciences, Boğaziçi Center. And I have many friends there, so I'm happy to be among you again. So today, I'm going to talk about Jordan algebras, but first maybe I have to say where my motivation came from. Well, there is one inspiring citation of Orhan Barut. When I was a student, we were learning representation theory from the book of Barut and Ronchka. Well, there is such a quotation: no definite connection is known at the present time between the use of de Sitter and conformal groups as dynamical groups or spectrum generating groups, and their use as space-time scale groups. And this was set in the Boulder conference in the 70s. I think that there's still things to, even nowadays, the progress in this direction is still not the terminal phase. I mean, there should things to be set. And now I'm presenting some connection between these two scales. So on one side, I'll have spectrum generating algebra, the hydrogen atom, and the other side, I'll have the space time symmetries, conformal symmetries of Minkowski space. So somehow you can think that this is interplay between large and small scales. And well, there are also hydrogen-like interpretations for the for other models, even composite models of particles, and I hope to have time. This is also idea of Barut. So it's the hero of today's talk, because I found many points which were gotten source of inspiration in his works. And well, in the broader sense, because he is not the only Turkish scientist in this talk, it is the title could be What I Have Learned from Barut, or What I Have Learned from the Turkish Mathematical Physicist School. So, well, here is some outline. First, I introduce the Jordan algebras, then, sorry, I want to keep going slowly. Yeah, first I introduce Jordan algebras, then I'm talking about their symmetries and the construction of Tate's counter and cohere of conformal algebra attached to any Jordan algebra. Then I'm going to talk about the oscillator realization of this conformal structure due to Murad Günaydın. And then I focus on my main example, which will be the 2x2 Hermitian matrices, or with complex entries. So I just take, you can think that you have the Pauli matrices. So, and then there are the two sides, there are two ways to connect two conformal algebras related to these Pauli matrices, Jordan algebra. And actually we'll see that one of these is like coordinate picture and the other is like momentum picture, and they fit exactly to the two, to the structure, conformal structure of Minkowski space in the spectrum generating algebra. And then I'll try to say a few words about the hadronic spectra, where the ideas of Barut also have some revival. Now, well, what is first? Pascal Jordan introduced the Jordan algebras in an attempt to axiomatize the quantum mechanics, so the algebra of observables, and he started by introducing symmetric products. So see, the problem with Lie algebras is that when you have two observables which are Hermitian, their commutator is not Hermitian. You have to put a 9 on the right side, hand side, and the commutator. But so somehow the Lie bracket is not closed and for the observables. So, well, you have if you introduce the anti-commutator, you can you have already this is Hermitian. If X and Y are Hermitian, this there is the product is Hermitian. Well, and then with this product, and you can understand. So the starting point is that you have some associative algebra, and you take the associative envelope of this algebra, and it turns out that there are quartic relations of this type. So we don't have the Jordan algebras are not associative, so that's but that's not reason to be afraid of them. So they're somehow more weird structures. Now, well, it was assumed in the beginning that there is underlying associative algebra, but we can get rid of this assumption and just take a commutative product with such relations. Well, it seems not very friendly as relation, but actually what is behind this is the power associativity, that if you have one observable, you can create powers, different powers, and expand exponentials. So so now I want to talk about the structure, and to every Jordan algebra you can associate a bunch of Lie algebra. So even one of the pioneers in this domain said that there's no Jordan algebras, there are only Lie algebras. Actually, you can reconstruct a Jordan algebra by its symmetries. So, so let me explain now the very basics of this symmetry. So first you define the Jordan map multiplication just by multiplication, or left or right doesn't matter because it is symmetric, so you choose one of those. Now there is a derivation on your Jordan algebra. In this is a linear operator satisfying the usual Leibniz rule. But the Leibniz rule can be rewritten, if you put this term on the other side, it can be rewritten as a commutator between derivation and multiplication in two different orders. And you see that this is again a multiplication only on the derived argument. So that to say that if you take derivations and multiplication, you can bind them together in something which is called structure algebra, And moreover, if you have, there is one Jordan identity following from the Jordan algebra relations. And if you, so if you have a commutator of two Jordan multiplications, this would satisfy this relation, but that is nothing but the Leibniz rule. So then you say that the commutator of two Jordan multiplication is a derivation. So you have a kind of super algebra where the even part is the derivations of the Jordan algebra, and the odd part is generated by the Jordan multiplication. And in the structure algebra, you have a center, which is just due to, we assume that we have a unit element in our Jordan algebra, so the multiplication by the unit element. And this later will come. So you have, you can factor the center, and then you have the so-called reduced structure algebra. Now, very important, somehow the core of the talk is in this Jordan triple product. If you have a Jordan algebra, then you can define a Jordan product just by this formula. And then the symmetry, using the symmetries of the Jordan algebra, you have this product as this flip symmetry, and also that that defining relation. Actually, you can consider a theory of Jordan triple system starting from here. So, well, once you have a Jordan algebra, you have a Jordan triple system. And with the help of this triple product, you define the linear map just by saturating. So the linear structure map, you can call it, it has two indices, and you saturate the triple product with that one. And as a particular case, you get the multiplication just when one of this argument is the identity. And then this complicated relation becomes a little bit more eligible. So you have you can interpret it as a commutator of this structure mappings. So here you see again, this is the triple product. And now, so these are now the Tits counter Coher construction is how to construct a Möbius algebra starting from how to construct a conformal algebra with the data of one Jordan algebra. Well, there is a conformal algebra, the structure, which is three-graded, the structure algebra that we have just defined is the zero component, and there are two copies. There are two copies of the Jordan algebra, which are understood as operators, which are commuting. So they're labeled, they're commuting between themselves. This follows from the grading. There is the three gradings. So if you commute this part, there's no other complements, and if you commute this part with itself. But if you commute this part with that part, you will have an element in the structure algebra, and and we have a conjugation that is keeping stable the structure algebra and is sending one degree into the positive degrees into negative degrees. And well, we have a structure here. We have a structure within these parts. Now, to have structures in the whole, we need to define, and so the structure algebra of the two, so to say, the two wings in the conformal algebra define again a structure algebra mapping, and here the action of the structure algebra on this is defined through the triple product. So and I learned this from United, so very clear presentation of the topic. And now, if you have a basis of your Euclidean algebra, so what is Euclidean? I have to say you have a condition for positivity. It's the old term is formal positivity. And now, and we consider finite dimensional ones. So now, these are structure constants of the triple product. Just as you define structure constants for the Lie algebra, you can define the structure constants, only the number of indices is different. And if you know the structure constants, you know the whole Jordan algebra. And so now in physics, we need representations. So if we have canonical commutation relations, we can construct a representation of the conformal algebra related to given Jordan algebra. So somehow from the data of of a Jordan algebra, we have a conformal algebra. We reconstruct everything. This is very nice, very compact way to see things. And so you'll see in a moment that if this seems too abstract, you know this into another form. You know this into another form. Well, if you have realization, so this is the whole so-called oscillator realization of conformal algebra. You starting from your canonical commutation algebra. So you need one Heisenberg algebra, so to say, to represent the Jordan algebra. So now, so you can do this for different Jordan algebras, and I pick up a table from Gunnagen. Only the language here is in group, not in algebra. So this is the restricted structure group, and this is the conformal group. And on the left are is the list of Euclidean Jordan algebra. So finite dimensional Jordan algebra with condition of formal positivity. And so you have these four series are Hermitian matrices with real complex quaternionic and octanionic entries. And here are the Jordan algebras related to Clifford algebras. Actually, I got interested in Jordan algebras when my supervisor, Michel Dubois-Violette, introduced me to the non-commutative exceptional geometry, which is also kind of revival of the ideas of Pythagoras. So the exceptional role of this here with the octanionic Jordan algebra is an exceptional member of the classification, and its symmetries seems to be related to the spectrum of standard model. So, well, this was too complicated for me, so I somehow wanted to have a simple example of Jordan algebra to work with. And such an example, what can be simpler than Pauli matrices that all physicists work on an everyday basis. So, well, Pauli matrices are representing the angular momentum, but on the other hand, with their anti-commutator structure, they define a Jordan algebra. And in this Jordan algebra, you have determinant, and the determinant, well, and the determinant is the well-known the Lorentz invariant, but this can be identified with a norm in the Jordan algebra. So we have a Jordan algebra with a norm. And now let us see that this abstract Tate counter-Kocher construction is actually providing you something that you know already. So, well, when you expand, these are derivation structure algebra, conformal algebra. When you exponentiate Lie algebras, you have the groups, you have automorphism, which are the exponentiation of derivations, and your structure group and conformal group. So, well, if you have this Hermitian conjugation similarity operation, or in other words, just binorial representation of a rotational group, these are automorphisms of your Jordan algebra. These are the automorphisms. So in the first place, if you take 2 by 2 Hermitian matrices, in the first place here you have SO3. Now, what is the structure group? What is the structure group? Sorry, I skipped. I have to be careful with the mouse. So what is the structure in the reduced structure group? Well, if you have the same, you have spinorial representation of Lorentz, and this is keeping, so you take the same operation as here. So these are conjugations, and now you have spinorial representation of Lorentz or double covering, and this is just a complexification of SU2. So this is, and well, this is the reduced part, and there is a trivial rescaling part due to the center. And this is due to the dilatation transformation. So if you multiply just by a factor matrix, real factor, you rescale your norm. You will not preserve your norm. So actually, the structure group, the reduced structure group is keeping the norm invariant, and this is giving the rescaling. So now you have also the conformal group, which arise as a Möbius fractional linear algebra. And so these are, this is forming SU22, or this is a double covering of SU24. Now, in this conformal algebra, you know that their Poincaré group is contained, and you have also you have the spatial conformal transformations. So, and I'll now bring this conformal algebra in the form which is familiar to you. So SO24 or SO6, if you take a positive norm, is just one orthogonal, pseudo-orthogonal the algebra here. You are choosing a metric in a 6-dimensional space with 2 pluses. And then actually, I think I have written this. So this is should be familiar for most of you. And so now the Tits counter cohere construction is giving this inclusion of symmetries. So the highest symmetry is the conformal one, and you have the Lorentz here, and you have just rotation. And so the generator of the reduced are the generators of Lorentz. These are angular momentum. These are 4 Lorentz. And then what you have, this right and left wing, which you have at the top of the structure algebra, are actually the translation and the conformal, special conformal transformations. And then you can just use the construction of Gunnagen for oscillator realization, and you'll get to a common place. You'll get to you can reconstruct some some result which was obtained from with other tools. These are so just to mention that here we are talking about groups, but we are not specifying the representation. So now we can look at the representations theory for a massless field of given helicity, and this was developed at the end of 60s by Gerhard Bach and Ivan Todorov, and Abdus Salam is also contributing to this. So then there is a work of Bach and Todorov, which is explaining some particular representation of the conformal group, which is just the same in these two different disguises. And now, and so, well, you have some conformal dimension, and all other terms are directly following from the Gunaydon's oscillator representation construction. So that is what I was fascinating first, that you somehow the Pauli matrices know about all of this structure. Once you fix your anomalous conformal dimensions, everything else comes out from the Pauli matrices and their Jordan algebra or their anticommutator. So, well, if you specialize zero, so these are, you have different representation, but these are the so-called massless field representation of given helicity. And if you specialize the helicity to zero, you are in the framework of the hydrogen atom. So this field is realizing a representation which is the hydrogen atom. Now I'll explain, but you can, when you look, there are other works of Barut and Borzan. You can also make use of the higher helicities, and this will be related to hydrogen atom, where you have magnetic, not only electric charges, but magnetic monopole and dion systems. So, well, why mass zero fields? Well, this is the photon carrier of the electromagnetic interactions. And so the world line of a photon is the zero length in so if two interacting particles are related by a light signal. So now let me briefly explain how to get to the hydrogen atom from the scratch. You have your Hamiltonian here written in some good units. Negative spectrum are bound states, discrete, and positive spectrum is continuous. And well, there's a separation of variables. You have radial equation, you have the spheric harmonics here, and you have the orbital number and the magnetic number. You can see this in any textbook. And so the radial Schrödinger equation is giving the energy states. From here you can get the energy states, but they have they depend only on the principal quantum number. So, well, you have degeneracy in every magnetic eigenvalue, which is 12 plus 1, but here the degeneracy is bigger, it's actually n squared. So you have some accidental, you have some hidden symmetry. Well, you can now, I want to write, and this, so I'm somehow revising the works of Barut and Borzan. So you can write your radial equation in terms of a algebra. So get rid of coordinates, having just a equation, algebraic equation. And there is one SO12 algebra, which is called radial, and actually it's changing. What it's doing, it is changing the principal quantum number. So it's interpolating between different quantum number. Well, for positive, you have another representation of the same algebra. This is the so-called discrete series. So for the positive spectrum, you have the principal series, which is continuous. Now,
Todor, I'm sorry, you have 5 minutes, okay?
Okay, thank you. So one of the generators in this radial algebra is the dilatation operator. So the result, the group action of this element is just rescaling. And you can rescale any operator in your theory. So the out means the rescale. So when you are performing rescaling operation on dimensionful quantities, you have some factors which are counting the dimension. So now you can rewrite your radial equation just with the radial algebra, and by using this similarity scaling transformation, you can actually rotate into the Lie algebra and get rid. So you can, by some simple rescaling, you can write this equation as some hyperbolic parameters here, and then by rotation you can eliminate one on the other. If you eliminate the non-compact one, you'll get the bound states. If you eliminate the compact coefficients, but it should be some other combination for the compact one, you have the continuous spectrum. So let's concentrate on the bound states. And so by rotating, you have you will get the principal quantum number, and you are solving the radial equation just from algebra. So, and now what about the extra symmetry, accidental symmetry? You have this Laplace Runge-Lenz. Laplace did it before, and after some rescaling, so conservation, this is conserving quantity, which is responsible for the accidental symmetry. So, well, the angular momentum, the Pauli matrices is represented, are giving the derivation of the Jordan algebra. So I try to look the structure from the point of view of Jordan algebra. So you have here the Runge-Lenz vector after some rescaling and modifying coefficients. So, and the SO4 symmetry is close between the angular momentum and the rescaled Laplace operator. Well, this SO4, where it comes from the point of view of Jordan algebras, you have some compact generators in the maximal conformal symmetry algebra. So, and the other one, SO2 part, comes from the principal quantum numbers. So somehow you have separation of variables here, and you have an n-square representation, dimension n-square SO4. Now you have other subalgebras. You have not only SO4, you have actually more than one. There's one Lorentz algebra between the currents and the rotations. And they're also a partner of Rungeland vectors, B. And well, you can put some very compact notation on the, here are the generators of the radio algebra, and here are the Rungelands and its partner, and so everything can be packed in a representation of SO to 6, and here. So here under the diagonal, you have just, this is there's our antisymmetric. This is not a nilpotent matrix. This is antisymmetric matrix. So this is the whole SO24. This is the whole SO24. And so the operators that we constructed through the Titz-Kocher counter construction can be placed in such a matrix. Here you see a block of the angular momentum. Here is the Lorentz block bigger. Here is the SO4 block. And here are, well, you can see the commutation of T3 with SO4 by looking at the block structure, and there are even more. And now, you have a grading in this by the counterpart of the dilation or scaling operator. And so the tree grading, when is done of the Rungelands vector and its partner, is giving that, well, these plus, positive, and minus part are not just, so they are related to Rungelands and its partner, but a combination of them. So difference and sum of these two vectors, Rungelands vectors, is giving the gradient part. So somehow you have here in the structure group you have Lorentz group with dilatations, sorry, and in the wings you have the combination of Rungelands and its partner. So well, and you see that the difference from these two is just a radius vector. So there is even a Galilean group, and that is normal as a subalgebra here. And this is normal because our problem is non-relativistic. But you have also a relativistic boosts, which are incorporated in that matrix. So, and now I just want to...
Maybe you should wrap up in 2 minutes.
Just, yeah, okay, thank you. So I want just to stress that we, I have introduced two different representations of the conformal symmetries of a Jordan algebra of 2x2 complex matrices. And actually, it was already understood, even in the works of Barut, that these are like X and like coordinate and momentum representation of one. They are related through Fourier transform. But now we have the Gunaiden oscillator representation, which is reproducing directly them. Only you have to change your oscillator algebra. So somehow there is I see the Jordan algebra as some unifying object here, from which you can expand, the whole conformal structure in two different seemingly unrelated cases. And so I want to say that this was just one example from the why this is interesting. We just got results which were known, but this is I see the Jordan algebra here as a unifying structure and a way to generalize. So this hydrogen atom and its partner, which is here the symmetry of Minkowski space, conformal symmetries, are just hidden in 2 by 2. So this is SU22 and SO2C. These are the symmetries of the algebra, Jordan algebra. And you can do this for the whole table. Actually, this is the counterpart of hydrogen atom, but, and it was, I found that this was done in a very nice way by Wovu Menk, only he haven't mentioned hydrogen atom in the title, so it was difficult to spot these results, but I recommend this too. Well, I'm out of time. I can just say that there is also Jordan superalgebras, and you can play the same game with Jordan superalgebras, and you will got results which are already, so for most of the cases, which are already known. But again, I think that the Jordan algebras here is giving a compact to, and so, well, maybe I stop here, and I don't want to abuse, or if there's some question, and I can make some more comments.
Thank you, Todor. So let's thank our speaker for this lovely talk. Okay, so are there any questions from the audience?
Yes. Hi, Todor.
Hello.
Nice to see you. It's a nice talk. Thank you very much.
Well, as always, I try
know
to say
everything
more
about the hydrogen atom, and you have shown that there are so many things that we have to learn about the hydrogen. But I wondered while I was listening, maybe you can apply the same techniques to positronium. Why not?
it is exactly. We are now exactly. This is. You can do even better. Actually, this is not specific to hydrogen. We are just using here that you have a compound system, nothing else. So you can apply this to positronium. You can take muon and antimuon and so on. But even more interesting, and that is something I would now comment on. You can apply this for mesons, because the mesons are compound particles. Well, they are not related by electromagnetic fields. There are some gluons, so there's some hadronic forces in between, but they are again hydrogen atom, in a sense. So they are hydrogen-like. And this direction of studies, that's why I was so inspired by Barut, was also initiated by Barut in the 60s, how to fit the spectrum of baryons, even not only 2 but 3 particles, with the SO2-4 symmetry. So and independently, I spotted an article from Mariana Kirbach. She's Bulgarian by origin, but she's working nowadays in Mexico. And she developed a model for the mesons, different mesons with very good fitting. So this model was not not initiated as just a theoretical speculation. On the contrary, it is based on the fit of particles or jet trajectories and the spectrum of mesons. And she has another one for the baryons, another series of papers, I mean. And so, but the fit of the results comes not on the hydrogen atom, so to say, on the infinite space, but on compactified. So you have the curved, you consider it on the place of three-dimensional space, you take three-dimensional sphere. This is a model that has been considered by Peter Higgs, one article which is not very well known.
Oh, yeah, I know that article, 1979.
Yes, yes.
One. Yeah.
And so now our effort, I try to understand the meson physics, but the idea is already in Barut, in the dynamical group of the curved Kepler problem or curved hydrogen atom. And somehow the curvature of this sphere is to be related to the finite range of interactions which are in QCD. And so only in the limit you have infinite space. So this is I think this is still ongoing, and there are many points which are not clear, but we see another representation of the SU24. See, in the Titz-Cantor-Kocher construction, you don't fix the representations, you fix the algebras are fixed. So by playing with the different representations, you can get to different physical systems.
Okay, I'm going to call you, Todor, next week. I don't have lectures, so I will call you after the conference.
With great pleasure.
Yeah, thank you very much.
Great pleasure.
Are there any questions?
I can ask one.
Yeah.
So mine is something like this. So Todor, can you assign a Jordan algebra to a classical system? Because you motivated the Jordan algebras in the beginning by making, Lie commutator of Hermitian matrices.
Yes.
You have to put an ISO and so forth. So thinking about the quantization procedure, can you start with a Jordan algebra associated to a classical system, then quantize it, and then obtain what you're
well, you see, here in that perspective, all the representation were the core is this Dunaidan oscillator construction, and it has in it already a Heisenberg algebra. So, well, this is a realization. It's already quantum by its structure. But on the other hand, I think that the answer it could be positive because, well, you can see that there is some Poisson structure behind. And so this should make sense only also on the this should make sense on the level of classical geometry, and then even I think that this interplay between symmetries of space-time and hydrogen atoms should be something like tangent and cotangent. This is an interesting to think. I think that Mank was using. I was not looking too much from this point of view, but I think he was mentioning the quantization procedure, so you can even write the things with on the pre-quantum level.
Thank you, Todor. Thank you for the talk as well.
Okay, thank you very much indeed. Çok teşekkür ederim sevgili arkadaşlar.
I have one last quick question.
Yes.
Okay, go.
First of all, let me thank you to, and you spent one of your summers to teach Gemini representation theory. So most of the stuff.
It was a lovely time.
Talk, I learned from you. Thank you for that too. My question is about this TKK construction. You associated a three graded Lie algebra structure to your Jordan algebra. Is there any analogous constructions for, like, we can take an L infinity or any other graded structure, like n-graded Lie algebras? Can we sort of pull back to have a higher dimensional
higher? There is a works of, I don't know how it's pronounced, this name, Palmquist or something. So there is a whole hierarchy in which these Lie algebras are the first blocks, and then you can expand this to infinite dimensional Lie algebras. So there's works in this direction. So so I don't know for L infinity, but certainly there is a. Do you mean L infinity in the sense of? In which sense you say L infinity?
Yeah, I just meant for any n, we can have like n many direct sum of Lie algebras. It doesn't have to tend to infinity.
Okay, well, I think that they're very sound generalization here in the direction of infinite dimensional Katz-Moody algebras, but also, well, you can think of expanding the matrix size, and you can think of infinite dimensional Jordan algebras, and there are also analogs of TKK construction there. Well, the only case which is for sight is the exceptional Jordan algebra. You don't have, you can't just expand this. This is a singular. That's why we believe that it can give exceptional answers.
Okay, thank you very much.
Thank you.
If you have any further questions, maybe you can send an email to Todor.
Yeah.
From now on. So let's thank our speaker again. Thanks, Todor, for accepting our invitation.